I give a talk about our recent work on cryptographic characterization of quantum advantage. This is a joint work with Tomoyuki and Takashi. You can see the full paper version on arXiv. Let's begin with the introduction. This work is about quantum advantage. It means the existence of some computational tasks that can be solved by a quantum polynomial time QPT algorithm, but cannot be solved by any classical probabilistic polynomial time PPT algorithm. Ideally, we want to obtain quantum advantage unconditionally. However, such unconditional results are beyond our current understanding of complexity theory. So we need some computational assumptions. Based on this current situation, we address the following question in this work. So what is a necessary and sufficient condition for quantum advantage? To study this question, we have to deal with quantum advantage more precisely. Especially in this work, we focus on protocols called inefficient verifier proofs of quantumness. Thus, I explain the definition of this protocol in the next part. Before defining inefficient verifier proofs of quantumness, let me begin with standard proofs of quantumness. A proof of quantumness, or POQ, is an interactive protocol between the prover and the PPT verifier that satisfies the following two conditions. The first condition is the completeness that requires a QPT prover can be accepted by the verifier with high probability. On the other hand, the second condition, soundness, requires no PPT prover can be accepted by the verifier with high probability. By this definition, POQ captures efficiently verifiable quantum advantage. On the other hand, the inefficiently verifiable variants of POQ are called inefficient verifier POQ or IVPOQ. IVPOQ are defined similarly as POQ, except for the behavior of the verifier. During the interaction, the verifier is the PPT algorithm, but after the interaction, the unbounded verifier decides to accept or reject. As I said earlier, we focus on IVPOQ in this work. This is our main result. In this work, we show that the existence of IVPOQ is equivalent to a cryptographic primitive called classically secure one-way puzzles. As far as we know, this is the first result that completely characterizes quantum advantage. Let me explain classically secure one-way puzzles. A classically secure one-way puzzle is defined as a pair of two algorithms, SAMP and bar. SAMP is a QPT sampling algorithm that outputs a pair of 2-bit strings, answer and puzzle. Bar is an unbounded verification algorithm that checks the input pair is correct or not. The security of classically secure one-way puzzles requires no PPT adversary that on input puzzle can output a correct answer that passes the verification. Now let's compare our result with the prior work. Morimae and Yamakawa showed classically secure one-way functions imply IVPOQ. On the other hand, we show that classically secure one-way puzzles imply IVPOQ. It is known that one-way functions imply one-way puzzles, but the inverse direction does not hold under some oracle. In other words, our result succeeds to obtain quantum advantage from the weaker assumption. Moreover, our result is tight because we show the equivalence between one-way puzzles and IVPOQ. I explain the implication of our result. Our result says that if there is no quantum advantage, then many cryptographic primitives are broken. To see this, let's draw the figure as follows. First, it is known that almost all classical cryptographic primitives imply one-way functions, and one-way functions imply many quantum cryptographic primitives, including pseudorandom unitaries, etc. Moreover, these many quantum cryptographic primitives imply classically secure one-way puzzles, and a primitive called EFI. In this work, we show the equivalence between classically secure one-way puzzles and IBPOQ. So if there is no quantum advantage, then IBPOQ do not exist, and therefore all cryptographic primitives that imply classically secure one-way puzzles are broken. As you can see in this figure, our result implies the interesting connection between the quantum advantage and cryptography. In the next part, I talk about proof overview. Before explaining the proof, let me remind the known or trivial implications. One-way functions imply one-way puzzles and IBPOQ, and moreover, you can easily check that non-interactive IBPOQ imply classically secure one-way puzzles and IBPOQ. The first step of our proof is to define the new primitive called quantum advantage samplers, or QAS, and show that QAS imply non-interactive IBPOQ. By using the result of step 1, we have the following two facts. The first one is one-way functions, or QAS, imply one-way puzzles, and the second one is one-way functions, or QAS, imply IBPOQ. Thus, to show the equivalence between one-way puzzles and IBPOQ, it suffices to show that both of one-way puzzles and IBPOQ imply one-way functions, or QAS. So we prove these directions as the second step and the third step. Actually, this proof overview and the proof sketch I will give you from the next slide are simplified for the clear presentation. So please see our full paper for the rigorous proofs. Let's begin with the first step. First of all, we define quantum advantage samplers, or QAS, as follows. A QAS is a QPT algorithm whose output distribution cannot be simulated by any PPT algorithm. By using this definition, we show that QAS imply non-interactive IBPOQ. This proof is inspired by Arnoson, 2014. Given a QAS, we construct a non-interactive IBPOQ as follows. The prover simply runs QAS and sends the output X to the verifier. The verifier checks as to if the Kolmogorov complexity of given string X is large enough or not. Here, the Kolmogorov complexity is defined as the minimal length of the program with which the universal Turing machine outputs X. If the result of this verification is yes, then the verifier outputs accept. Otherwise, the verifier outputs reject. Then both of the completeness and the soundness follows from the basic properties of Kolmogorov complexities. Now we have these implications. So let's go to the second step. The second step is to show that one-way puzzles imply one-way functions, or QAS. For the sake of contradiction, assume that both of QAS and one-way functions do not exist. Then in the definition of one-way puzzles, we show that QAS imply one-way functions, or QAS. the QPT sampler can be replaced with a PPT algorithm because QAS do not exist. Then the primitives become totally classical and same as one-way functions. Therefore, the security of the primitive is broken because we are assuming that one-way functions do not exist. Finally, let me explain the third step. The third step is to show that IVP or Q imply one-way functions or QAS. This proof is inspired by Ostrovsky in 1991. Again, for the sake of contradiction, let's assume that both of QAS and one-way functions do not exist. Then the whole transcript of the interaction of IVP or Q can be sampled by some PPT algorithm B, because QAS do not exist. By using such PPT algorithm B, we construct a PPT prover that breaks the soundness of IVP or Q as follows. In the ith round, the PPT prover takes the exchanged messages as input, and it computes the randomness R, with which the PPT algorithm B outputs the transcript that is consistent with the given messages. This is possible because we are assuming that one-way functions do not exist. After that, the prover uses R and run B to obtain the ith message mi and output mi. By repeating this, the PPT prover can simulate the behavior of the QPT prover and breaks the soundness of IVP or Q. This is a summary of our main result. We show the equivalence between the IVP or Q and classically secure one-way puzzles. As I said, this is the first time to obtain the complete characterization of quantum advantage. In the next part, I introduce our additional results. We have 3 additional results. First, we show the equivalence between interactive sampling-based advantage and interactive search-based advantage. Second, we show the robustness of the definition of IVP or Q. Finally, we study IVP or Q with zero-knowledge property. The first additional result is the equivalence between sampling-based quantum advantage and search-based quantum advantage in the interactive setting. Before discussing this result in detail, I briefly review the sampling-based and search-based approaches to quantum advantage. First, the sampling-based advantage means the task of sampling from a distribution D can be solved by a QPT algorithm, but cannot be solved by any PPT algorithm. In terms of the computational complexity, sampling-based advantage is expressed as samp B QP not equal to samp B PP. Second, the search-based advantage means the task of finding a bit string X that satisfies some relation R can be solved by a QPT algorithm, but cannot be solved by any PPT algorithm. In terms of the computational complexity, search-based advantage is expressed as FBQP is not equal to FBPP. Interestingly, it was shown that these are equivalent by Aronson. In this work, we show that this equivalence holds even in the interactive setting. The important observation is IVP or Q capture interactive search-based advantage by the definition. We define a primitive called interactive quantum advantage samplers, or IntQAs, that capture interactive sampling-based advantage, and show that IVP or Q are equivalent with IntQAs. This is an interactive version of the equivalence between sampling-based advantage and search-based advantage that was shown by Aronson. The definition of int QS is as follows. An int QS is defined as a pair of two QPT algorithms that interact over a classical channel, such that the distribution over the transcript cannot be simulated if at least one of them is PPT. Next, I explain the result about the robustness of IBPOQ. We introduce two variants of IBPOQ. The first one is public coin IBPOQ. As I explain later, in this protocol, the computational power of the verifier is weaker than the standard IBPOQ. So public coin IBPOQ implies standard IBPOQ trivially. The second variant is quantum verifier IBPOQ. In this protocol, the computational power of the verifier is stronger than the standard IBPOQ. So the standard IBPOQ implies quantum verifier IBPOQ trivially. We show that both of these variants are equivalent to standard IBPOQ by showing two red directions. These results says the definition of IBPOQ is robust to the choice of the computational power of the verifier. The definition of public coin IBPOQ is as follows. In this protocol, the verifier during the interaction is public coin. In other words, the verifier always outputs random bit string. So clearly, this verifier is a special case of PPT verifier. And we define quantum verifier IBPOQ as follows. In this protocol, the verifier during the interaction is QPT larger than PPT. So clearly, the standard IBPOQ is a special case of this quantum verifier IBPOQ. Finally, I explain the result about zero-knowledge IBPOQ. Zero-knowledge IBPOQ satisfies additional condition called zero-knowledge property. This property requires the transcript of the interaction can be simulated by the PPT simulator. Depending on the strength of zero-knowledge property, we can consider computational zero-knowledge and statistical zero-knowledge. In this work, we show that statistical zero-knowledge IBPOQ imply classically secure one-way functions, and classically secure one-way functions imply computational zero-knowledge IBPOQ. These results mean the rough equivalence between one-way functions and zero-knowledge IBPOQ. Let me summarize my talk. This figure represents our results. Our main result is the equivalence between one-way puzzles and IBPOQ. As I mentioned earlier, this is the first result that completely characterizes quantum advantage. Moreover, we show the additional equivalence between IBPOQ and IntQAS. This result says even in the interactive setting, the sampling-based advantage and search-based advantage are equivalent. Finally, we introduce several variants of IBPOQ. The equivalence between IBPOQ, public coin IBPOQ, and quantum verifier IBPOQ says the definition of IBPOQ is robust to the choice of computational power of the verifier. And the result about the zero-knowledge IBPOQ means that rough equivalence between the classically secure one-way functions and zero-knowledge IBPOQ. That's all. Thank you.